In this module, we're going to discuss the cash account and the pricing of zero coupon bonds in the context of the binomial model for the short rate. The cash account and zero coupon bonds are extremely important securities in derivatives pricing in general, and so we're going to spend some time now figuring out how to price them and understand the mechanics of these securities. So let's get started. If you recall, this is our binomial lattice model for the short rate. Or I is the short rate that applies for lending between times I out to I plus 1. In general, it's a random variable because it can take on any of these values, for example, at time 2. So at time t equals 2, the short rate R2 could take on this value at state 0, this value at state 1, or this value at state 2. We also have our risk-neutral probabilities, QU and QD, and of course QU plus QD must sum to 1. These are our risk-neutral probabilities, so they're strictly positive, and what we will do is we price everything with these risk-neutral probabilities. In particular, for example, if we want to price a non-coupon paying security, and I use the term non-coupon here loosely, so a coupon could refer to any cash flow. So if we want to price a non-coupon paying security at time I state j, well, we just do our usual discounted risk-neutral pricing. So Zij, the value of the security at time I state j, is 1 over 1 plus the short rate at time I state j times the expected value of the security one period ahead, where we take that expected value with respect to the risk-neutral probabilities Qu and Qd. Now, as we said as well before, there can be no arbitrage when we price using 3. And the reason for that is as follows. If you recall our definition of a type A arbitrage, for example, so a type A arbitrage was a security of the form V0 being less than 0 and its value at time 1, V1, must be greater than or equal to 0. So we said any security like this in a one-period model constituted a type A arbitrage. Well, this is not possible over here if we price everything according to 3. And the reason is, so Z will take the place of our V here. We see that it is not possible for this to be greater than or equal to 0 and this to be greater than or equal to 0 and yet have this being less than or equal to 0. This is not possible because the Q's and R are all strictly positive. And if the z's are greater than or equal to 0, then this must be greater than or equal to 0 as well. So we actually cannot get a type A arbitrage. That's not possible. It's the same for type B. If you recall, a type B arbitrage assumed a security of the following form: V0 less than or equal to 0, V1 greater than or equal to 0, but V1 not equal to 0, which means that V1 is greater than or equal to 0 in all states, and there's at least one state where it's actually strictly greater than 0. Well, again, the exact same argument over here would show that that is not possible as well. So there can be no arbitrage when we price according to 3. I now want to talk a little bit about the cash account. The cash account is a particular security that in each period earns interest at the short rate. We're going to use BT to denote the value of the cash account at time t, and we will be assuming without loss of generality that it starts off with a value of 1, so B0 is equal to 1. The cash account is not risk-free, and the reason it's not risk-free is because interest rates are uncertain. They're stochastic. In particular, the value of the cash account at time t plus s, say, is not known at time t for any value of s greater than 1. However, it is locally risk-free because I do know the value of bt plus 1 at time t. In fact, bt plus 1 will always be equal to bt times 1 plus the short rate. And I'm going to know this short rate at time t, and therefore I will know bt plus 1 at time t. So again, think of your bank account analogy. If I deposit money today for 1 month, I know what rate will apply for that 1 month period, and so I will know how much I will get at the end of the month. But I will not know what interest rate will prevail in 1 month's time, and therefore will not know future values of the cash account beyond 1 month. So a quick thing to notice here, so bt therefore has this expression here. Based on the argument I just gave you, I can look at bt plus 1 and bt and divide one by the other and see that I get 1 over 1 plus rt. And the reason I want that expression is down here. I want to derive equation 4 here. So how do I derive equation 4? Well, again, for a non-coupon paying security, zt at time t, state j, is equal to 1 over 1 plus rtj times the expected value of the security 1 period from now. So this is our familiar risk-neutral pricing expression from the previous slide. I can actually rewrite this expression as the expected value under Q Remember, Q is equal to QU and QD, the risk-neutral probabilities. And I can replace my 1 over 1 plus RTJ with this expression here, BT over BT plus 1. So therefore, I can write the value of the non-coupon paying security at time t as being the expected value at time t under Q of ZT plus 1 multiplied by BT over BT plus 1. So rewriting equation 4, I can just bring the BT over to the left-hand side and I get this expression here. This is an important expression, but I can go a little bit further. I can actually iterate it to get the following. So for example, I can write ZT over BT is equal to ET under Q of, well, we know it's ZT plus 1 over BT plus 1, but I can actually use this equation 5 again to write ZT plus 1 over BT plus 1 as the expected value under Q, conditional on time t plus 1 information, of ZT plus 2 over BT plus 2. And using the law of iterated expectations, this is equal to the expected value conditional on time t information of ZT plus 2 over BT plus 2. And I could repeat the same trick again and again, and so it's easy to see that this condition is held. So this is our risk-neutral pricing condition for a non-coupon or non-dividend paying security. In particular, it's the pricing equation that we use for any security that does not pay any intermediate cash flows between times t and t plus s. When we're doing risk-neutral pricing for a coupon-paying security, we use the exact same idea. So ZTJ equals 1 over 1 plus RTJ times the expected value under Q of the value of the security plus the cash flow at time t plus 1. So that just gives us this expression here. And for the same reason as before, we can see as long as we price any coupon-paying security this way, there cannot be an arbitrage. There is no way that this quantity can be greater than or equal to 0 and yet to have ZTJ being less than 0. So you couldn't have a type A arbitrage, because if this is greater than or equal to 0, the risk-neutral probabilities we know are strictly greater than 0. This is greater than 0, and so all of this expectation must be greater than or equal to 0. So in particular, this is not possible. So you couldn't get a type A arbitrage, and for the same reason, you couldn't get a type B arbitrage as well. All right, so we have 7. Well, it's easy to rewrite 7 using the same idea as we used in the previous slide. I can replace 1 over 1 plus RTJ with BT over BT plus 1, bring the BT over to the other side, and I get expression 8. Now I can iterate, I can substitute in, for example, if I substitute in the following, I know that ZT plus 1 over BT plus 1 is equal to the expected value under Q, conditional on time t plus 1 information, CT plus 2 over BT plus 2 plus ZT plus 2 over BT plus 2. So if I substitute that in down here, I'm going to get this expression here when s equals 2. And it's easy to see that this expression holds more generally for general values of s, or for integer values of s greater than t. So this is an extremely important condition. We're going to use this throughout this section on term structure models and pricing fixed income derivatives. It tells us how to price fixed income derivatives using risk-neutral pricing, and this ensures that there's no arbitrage. In other words, it ensures that we're pricing fixed income derivatives in a manner which is consistent with no arbitrage. Note also that equation 6 is actually a special case of 9, because we get equation 6 from 9 by just taking all of these CJs equal to 0. So this is an extremely important result. It guarantees that we can price everything with no arbitrage. Here is a sample short rate lattice. It starts off with the short rate, or 0, 0, being equal to 6%. And then the short rate will grow by a factor of u equals 1.25 or fall by a factor of d equals 0.9 in each period. It's not very realistic. These interest rates, as you can see, grow quite large here. And given the current economy, global economy, where interest rates are very low, this example wouldn't be very realistic. But it is more than sufficient for our purposes. In fact, it's good to have such a wide range of possible interest rates, as it makes it easier to distinguish them in the examples that we'll see in the future. At this point, I should also mention that you should look at the spreadsheet that is associated with these modules. The spreadsheet, you'll see this particular example there, and we're going to be using this example throughout this section to price various types of fixed income derivatives. We're going to be looking at caps, floors, swaptions, options on zero coupon bonds, and so on. So we're going to use this particular short rate example as our model in all of these pricing examples. So the first thing we're going to do is we're going to see how to price a zero coupon bond that matures at time t equal to 4. So if we want to do that, we're going to use our risk neutral pricing. Our risk neutral pricing result, if you recall, states that ZT over BT is equal to the expected value conditional on time t information of ZT plus 1 over BT plus 1. And this is our risk neutral pricing identity for securities that do not pay coupons or do not have intermediate cash flows. And certainly that is true of a zero coupon bond. If you recall, a zero coupon bond does not have any intermediate cash flows. It only pays off its face value at maturity. In this example, maturity is at t equal to 4. This face value is 100, and this indeed is, if you like, using our notation for zero coupon bonds, Z44. So what we're going to do is one way to price the zero coupon bond is to use this expression here by just working backwards in the lattice one period at a time. We know Z44, it's 100 at maturity, the bond is worth 100. So let's work back and compute its value at time t equals 3. Well, to do that, we can just use this expression. Another way of saying this, and we saw this as well before, this is equivalent to saying that ZT is equal to the expected value at time t of ZT plus 1 over 1 plus RT. And so in fact it's this version that we're going to use. We're going to work backwards, computing the value ZT at every node by discounting and computing the expected value one period ahead. So that's all we're doing here. So for example, the 83.08 that we've highlighted here is equal to 1 over 1 plus the short rate value at that node. And if we go back one slide, we'll see the short rate value at that node was 9.38%. So that's where the 0.0938 comes from here. And then it's the expected value under Q of the value of the zero coupon bond one period ahead. There are two possible values, 89.51, 92.22, and that's what we have here. So we just work backwards in the lattice one period at a time until we get its value here at time 0. And this is Z04, the time 0 value of the zero coupon bond that matures at time 4. Having calculated the zero coupon bond price at time 0, we can now infer from that the actual interest rate that corresponds to t equals 4. In particular, if we assume per period compounding, and we let S4 denote the interest rate that applies to borrowing or lending for 4 periods, then we know that 77.22 times 1 plus S4 to the power 4 must be equal to 100. And so, of course, we can invert that to get that S4 is equal to 100 over 77.22 all to the power of 1/4 minus 1. And so that's how we get S4. So there's always a one-to-one correspondence between seeing the zero coupon bond prices and seeing the corresponding interest rate. Therefore, it means that we can actually compute all of the zero coupon bond prices for the 4 different maturities. So we can compute the zero coupon bond price for maturity t equals 1, t equals 2, 3, and 4. And from this, we can actually back out the actual interest rates that apply to these periods. So for example, we will get a term structure of interest rates that looks like the following. We have t down here, and we've got the spot rate, ST here, and maybe we'll see something like the following, or maybe it's an inverted curve. But this point here, so for example T1, that point corresponds to there, and it corresponds to some spot rate ST1 there. So we can actually use this model to price all of the zero coupon bonds, and from all of these zero coupon bond prices we can invert them, as I did in the previous slide, to get the term structure. The term structure is the term structure of interest rates. We can see what interest rate applies to each time t. At time t equals 1, for example, we will then compute a new set of zero coupon bond prices and obtain a new term structure. So for example, at time t equals 0, we're down here. But at time t equals 1, maybe I'm up in this state of the world. So if I'm up in this state of the world, I could recompute the term structure of interest rates. I could do that by pricing all the zero coupon bonds at this point. I'm going to get a different set of prices to the set of prices I had at time t equals 0, and I can invert this new set of prices to get a new term structure, and maybe that new term structure will look different. Maybe it will look something like this. So I will get a new term structure at time t equals 1. Moreover, the term structure I see will depend on whether I'm up here or down here. So what we've actually succeeded in doing is defining a stochastic model or a random model for the term structure of interest rates by just focusing on the short rate. So the short rate RT is just a scalar random variable or a scalar process. By focusing on modeling the short rate as we've done, we've actually succeeded in defining a stochastic or random model for the entire term structure. And that's actually a very significant point to keep in mind when working with these short rate models.